My dear students, like I promised you in the previous lesson, we are starting a new chapter. The chapter is still in the mechanics part, paper 1 for physics A-level, and we are now looking at simple harmonic motion. Simple harmonic motion. So there are different models. I will be able just to make a simple illustration. But since here I will not be able to use some of the devices all the apparatus that you have in the laboratory, I will make some demonstration. I will just show you a video that you can look at how simple harmonic motion is displayed. But just simply telling you, you may have, like some of you have been on swings before, yeah, swings. You would maybe move your sister or brother to some side and you release them. So they go, come back, go, come back. That kind of motion is exhibiting simple harmonic motion. Simple harmonic motion. Or you may have a spring onto whose free end, it may be a clamped spring, helical spring actually. Like you have a spring, and the free end you attach a mass. So you displace it through, because we are assuming that that's where it had rested after getting an extension. Displace it through a small distance, which you can call x, and then you release it. Of course, when you release it, what will happen? It will start oscillating. We call that oscillating. So it starts not dancing, but oscillating. You've done that before. You've done that before. So let me show you. I'm going to request the producer to show us something. Let's all have a look at this. Yeah, like you can see here, we are having a particle. Actually, we have a mass that is attached on a spring, and there is a tape onto which it is now, because some pen is attached onto it, it is able to draw some kind of line. But you see that it now makes a wave. For it, it's just moving up and down, up and down. It's just moving up and down. If I put here, you see, in just one vertical line, it's moving up and down. But it's able to, if you look at the kind of wave that is making, the drawing, it's a wave. It's making a wave. So we are going to study simple harmonic motion, bearing in mind two concepts. Bring ideas from circular motion, and then also bring ideas from the wave motion that you learned in O-level. So this is just a basic model for you to understand this type of motion. Alright. So let's start now by writing down the definition. What is simple harmonic motion? What is simple harmonic motion? So we define simple harmonic motion using its equation. We shall see the equations in detail later. But just understand that if you have an object, and maybe it's attached on a spring. Maybe let me assume two springs. There's spring 1 here, then another spring 2, like this. So these are fixed ends. If you displace it to the right, displace it, of course this is the equilibrium position. Displace it to the right and then you release it. It will start performing simple harmonic motion. It will oscillate like this. So about a fixed position. So we define simple harmonic motion using an equation. which is A, in terms of its acceleration, equals to negative omega squared x. A is equal to negative omega squared x, where A is the acceleration. Sometimes we can just write acceleration as the second derivative of the displacement. Now x, A or x dot dot, this one here is the second derivative. This one here is the second derivative of the displacement, and it means acceleration. X is the displacement of the body that is executing simple harmonic motion from its equilibrium position. Omega is, of course, omega, you know what omega is, the angular frequency. So we are going to define simple harmonic motion by using this. We say simple harmonic motion is the motion of a body whose acceleration is directly proportional to its displacement from a fixed point. That's the equilibrium point. And the negative shows us that that acceleration is always directed towards that point. So we say simple harmonic motion. Simple harmonic motion. You can always just abbreviate it as SHM. It's the standard abbreviation. Simple harmonic motion, or simply SHM is the motion of a body whose acceleration is directly proportional to its displacement from a fixed point, and is always directed towards that point. That acceleration should always be directed towards that point. Why did I start by writing the equation? Of course, I would have started straight away by writing the definition first. But I wrote the equation because if you remember the equation, you can easily define simple harmonic motion. X is the displacement from the equilibrium position or from that fixed point, and omega squared has a negative. This negative shows that acceleration is always directed towards that point. Why is it a negative? Remember, acceleration and displacement, the two are vector quantities. So for them to be in opposite directions, it means that there has to be a negative to cater for the opposite directions. Okay. Now, what are the characteristics of simple harmonic motion? So we say we can still use the definition, by the way. We can still use the definition to look at the characteristics. I'm going to abbreviate it. Characteristics of simple harmonic motion. From what we've heard in the definition, please understand that the acceleration is directly proportional to the displacement from a fixed point. So we are saying that the acceleration is directly proportional to the displacement from a fixed point. Please write this. This means acceleration. This means displacement from a fixed point. Actually, to make it better, let me write it. Because some people will just quote it minus telling us what it is. The acceleration for simple harmonic motion. The acceleration is directly proportional directly proportional to the displacement. Acceleration, actually, because it keeps varying. Directly proportional to the displacement from a fixed point. Next, still in the definition, there is some other part. We said that acceleration is directed towards that point. So you can go on and say that its acceleration is always directed towards a fixed point. The acceleration is always directed towards that fixed point. The fixed point is the equilibrium point. Next, understand that in simple harmonic motion, mechanical energy is conserved. Mechanical energy is conserved, and of course, if you, like you did in O level for oscillations, that motion is periodic. So it is periodic. That motion is periodic. Then lastly, mechanical energy is conserved. For you to have perfect simple harmonic motion, mechanical energy has to be conserved. Otherwise, if mechanical energy is not conserved, energy will be drawn out of the system, especially by like dissipative forces, and of course the amplitude of the simple harmonic motion will keep reducing until the body finally settles. So that's the definition, and those are the characteristics of simple harmonic motion. Now we're going to look at one case as we summarize the beginning part of the introduction. So please understand that simple harmonic motion is actually related to circular motion. So we shall be using similar terms. Yes. Now, consider a periodic motion of a body along a straight line with acceleration of the particle always proportional to its displacement from some fixed point and always directed towards that point. I will take the same case that I had. So consider simple harmonic motion of a body of mass m, about a fixed point O. So this is our body. It has mass m, and it's moving. Let me take the case where I have a smooth horizontal surface, and I have, you can have different cases. Let me illustrate to you. Okay. If I look at the models, they will confuse someone. Let us assume that this body, I will not consider the forces that are causing its motion. This body is moving from point O, this is point O. It's moving, executing simple harmonic motion. It moves like this, executing simple harmonic motion. So it is moving between 2 points. There is a point P here and P prime. P and P prime. We want to look at a case where, if this is the equilibrium position, displace that body. We take it through a displacement. A displacement x. So give it a displacement, like not really giving it, but of course it's moving. The amplitude from the equilibrium position to the point where it stops momentarily before returning. This part here. This is the amplitude. So this body is moving like this. I'm ignoring the forces that are responsible for its motion. We are looking at the generic example. It's executing simple harmonic motion. You realize that at the equilibrium position, the velocity is maximum. Then it decelerates, stops a bit, returns this way. Here, it accelerates. When it reaches here, decelerates until the velocity is 0. Then it accelerates. When it reaches here, velocity is maximum, decelerates. So it's like this. Keeps executing simple harmonic motion. So we want to consider this body and look at a few of the terms that we use in simple harmonic motion. The body is at point B here, and at point B, the displacement from the equilibrium position is x. The amplitude is A. Now, do you know that while it's going the other side, the restoring force will try to pull it back, so it ends up retarding or decelerating until the velocity is 0. Then it's pulled back. While coming back, of course, the displacement will be negative. Always the acceleration and the displacement are opposite to each other. When it's going the other side, positive displacement, it will be decelerating, meaning the acceleration is negative. When it's returning, while it's accelerating, it will have a negative displacement from here. It will have a negative displacement. So they are always, in simple terms, they are always having their opposite. Negative meaning that displacement is in this other direction. So since the acceleration is always directed towards O, the particle's speed will decrease as it approaches P prime. Yes? And also as it approaches P. The acceleration will then cause it to travel back. So when it reaches here, the acceleration causes it to travel back. Through O to just reach point P. And then return through O again to reach point P prime. This process continues as the particle oscillates about O. So at points P and P prime, the particle will have 0 velocity. Please observe that at the ends here. At P and P prime, the velocity is 0. So where is velocity maximum? The velocity is maximum at the equilibrium point. So at O, the velocity is maximum. Please observe that the velocity is maximum at point O. Now the distance OP prime is what we call the amplitude. Distance OP, which is equal to OP prime, is what we call the amplitude. Is the amplitude. Definition, the definitions we shall look at them. So the equilibrium position, that's the equilibrium point O, is a point in the path of a particle executing simple harmonic motion where the particle comes to rest at the end of the oscillations. After all oscillations are done, where it settles, that is what we call equilibrium point or position. And at the equilibrium position, the particle has no acceleration. Here, at O, the velocity is maximum, of course a maximum, implying that the acceleration is 0. acceleration is 0. Meaning that acceleration is maximum at the points P and P prime. Acceleration is maximum at those ends. Maximum. Okay, now in the next lesson, I am going to explore, we're going to pass through the terms that we use in simple harmonic motion, and then we go on to the equations that are used in simple harmonic motion. Thank you very much. Let's now dive into lesson number 2. Thank you.